So let's proceed in the very challenging task of characterizing petrophysically the fractures. This is the second presentation dedicated to this subject. Let's start again from the issue of the fracture length, already considered in the last slides of the former presentation. The issues of the fracture length could be faced also, let's say, from a more speculative approach based on the observations that we can make on outcrops. On outcrops, we can see fractures having a variety of heights, but very often they show large number of short fractures and relatively few tall fractures, suggesting a kind of log normal or exponential or power law distribution. These scenarios are described by the two plots on the bottom of the slide, showing the fracture height frequency that could be interpreted as a log normal or exponential distribution, or as a power law distribution as suggested by the plot on the right, that is, fracture height versus cumulative frequency. This kind of observation can be made much more hardly about the fracture length because of the need of a very extensive horizontal outcrop that generally are not available. However, working on the seismic volumes, similar observation can be made considering the estimated seismic fault length, as here described by fault polygons on a depth slice. So, when supported by the available data, the issues of the fracture length could be faced, at least statistically, also from a more speculative approach, considering the fracture population observed at different scales, from the seismic fault to the small fractures of the cores, as genetically linked to the same tectonic stress, a kind of tectonic continuum model. The conceptual model could be that the whole fractures population is characterized hierarchically by smaller fractures representing a kind of damage zone of the larger events, and correlated for location, dimension, and intensity. So the speculative assumption could be that all these kind of discontinuities, large to small, belong to the same family, and are characterized by a kind of exponential relationship between their length and height versus the cumulative number, as illustrated by this log-log plot. The total fracture population would be made hierarchically by an increasing number of the smaller event according to an exponential distribution that is inferable from the larger events, like the seismic faults. In fact, sometimes the cumulative frequency plot of the fault's length in the log-log graph depicts a power law linear trend in the central region that is lost at the short and the long ends. This fact could be explained by the non-representative sampling near the tails. The smallest fractures are in fact hardly visible on seismic and so could be undersampled. The largest ones can exceed the sampling area and so could be incomplete. So, neglecting the tails, an exponential correlation can be defined and utilized to drive the distribution of fracture numbers and length in the stochastic simulation. It can be utilized to cover the fracture population range of length in between the lower limit of the seismic fault's resolution and the higher limit of the core's resolution. In fact, we could assume that the small fractures included at the core plug scale of observation could be theoretically already described in the rock matrix characterization on the basis of the routine core analysis. The exponential correlation can be so utilized to drive the distribution of fractures number and length in the stochastic simulation. So, from a speculative point of view, we could consider the fracture population's properties like number, length, age, aperture, and permeability all together linked. For example, from the false polygon interpreted on seismic, we could guess information about fracture length and their cumulative number distributions. Then, the fracture age could be inferred being likely correlated to the fracture's length, generally shorter being confined by mechanical changes at the bed boundaries. Then, the effective fracture aperture should be likely correlated to the fracture length, and in turn, the aperture correlated to the fracture permeability. The huge uncertainties affecting all the steps can be minimized by a backward calibration from the permeability estimated at the well, tuning accordingly the different correlations. The definition of the length of the fractures is very uncertain, but destined to have a great impact on the fluid flow path. The simplest approach could be the assumption of an average value as guessed from analogs or from any other available source or geological concept. However, to try to mimic the geological complexity observed on the outcrops, we could assume a log-normal distribution or a power law distribution truncated at the lower limit corresponding to the core scale of observations. Considering these two later scenarios, made by fractures of different length more realistic, the aperture should be theoretically correlated to the fracture length. That means longer the fractures, wider the aperture. Assuming a kind of penny-shaped average fracture aperture, this correlation is described by this kind of formula, where the fracture's aperture is related to the fracture length according to a parameter that we call alpha. However, this growing trend is expected to be confined because the larger fractures should be the result of the coalescence or merge of small fractures rather than just a single growing event. Therefore, considering analog outcrops data, a confining cap value should be assumed. Considering the correlation between permeability, aperture, and length, we can try to calibrate this correlation going backward from the measured KH, from well test or production behavior. However, we have to refer only to the fracture's contribution. That means a KH value net of the contribution of the rock matrix. Therefore, the rock matrix KH, once estimated for each well in the area investigated by the well test, has to be subtracted from the total estimated well test KH to get a kind of fracture net KH that is the target of the discrete fracture network calibration in the 3D model. The workflow considers the fractures affecting the well region investigated by the well test and tunes by iteration an initial relationship length versus aperture to match the estimated fracture net KH. At each iteration, the discrete fracture network permeability is upscaled in the 3D grid model and compared with the relevant fracture net KH that is the target to be hit. In fact, in the workflow tries to calibrate the fracture network with the dynamic data, focusing the attention only on the fracture characteristics, but keeping the discrete fracture network realization fixed. The analysis is performed separately, well by well, based on the relevant network of fractures that is part of the total discrete fracture network built at field scale. Therefore, the possible different effective fractures aperture versus length correlations affecting the different wells and so the different areas of the field are estimated. The workflow applied on each sector model is here sketched. A discrete fracture network effective aperture estimation is performed according to an initial relationship fracture length versus aperture using a penny-shaped correlation as per Olson paper. The discrete fracture network permeability is estimated according to the fracture aperture using the cubic law. The discrete fracture network permeability is upscaled using the autocorrected algorithm that is quite fast, and the KH fractures estimation is performed. A comparison between the initial estimated fracture net KH that represent our target with the KH fractures coming from the upscaling of the fracture permeability is performed. A final match of the fracture net KH by revising the initial relationship between fracture length and effective fracture aperture is performed, tuning the penny-shaped correlation, that means tuning alpha. An additional issue that is likely to impact on the fracture's aperture and thus on permeability and anisotropy of the fracture network is the maximum horizontal stress orientation, or better, the orientation and the ratio between the maximum and minimum horizontal stresses. They are bound to impact on the apertures of fractures that are mainly vertical events. In fact, fractures parallel to the maximum horizontal stress are bound to be affected by a larger aperture with respect to the fractures perpendicular to the maximum horizontal stress. To take into account this possible impact of the present maximum horizontal stress orientation, a variation of the relationship length versus aperture is considered in relation to the fracture strike. A gradual reduction is considered according to the increasing angle, delta azimuth, between the maximum horizontal stress and the fracture strike, using a kind of tuned cosine function. The maximum reduction at the perpendicular condition, that means delta azimuth equal to 90 degrees, has to be guessed considering analog, geomechanical data, the ratio between the horizontal stresses, and in some cases in relation to interference test. This reduction generally is assumed between 0, that means no reduction with isotropic horizontal stress, up to 100% of the maximum length versus aperture correlation. That means that fractures perpendicular to the maximum horizontal stress are closed. In this specific case, for example, a 60% aperture reduction has been assumed. In the iterative workflow illustrated in the former slides, the highest length versus aperture relationship is so assigned to the fractures oriented parallel to the maximum horizontal stress, with a gradual change of the correlation length versus aperture in relation to the delta azimuth. The workflow implemented on each well gives as output the different optimized length versus aperture relationship described by alpha, able to match the observed fracture net KH in relation to the estimated discrete fracture network characteristics, that means fracture intensity, length, and also orientation. In this approach, the iterative workflow is the same formally illustrated, but the tuning of the length versus aperture correlation is replaced by the tuning of a kind of clouds that mirrors the increasing angle, delta azimuth, between the maximum horizontal stress and the fracture strike. The highest length versus aperture relationship is so assigned to the fractures oriented parallel to the maximum horizontal stress, with a gradual change in relation to the delta azimuth. The initial cloud is so tuned by an iterative process to hit the target represented by the estimated fractures net KH. In the iteration, the reduction of the contribution of the fractures with the delta azimuth larger than 0 is balanced by the increment of the length versus aperture cloud general trend. The workflow implemented on each well gives as output the different optimized length versus aperture cloud, able to match the observed fracture net KH in relation to the estimated discrete fracture network characteristics. The maximum horizontal stress could impact on fracture permeability and fracture network anisotropy, confining the most effective fractures to the orientation about parallel to the present maximum horizontal stress. However, the estimation of the fracture aperture reduction is very uncertain. If some interference test is available, the maximum reduction at the perpendicular condition, that means delta azimuth equal to 90 degrees, can be introduced in the iterative process and tuned to be calibrated by matching the observed data that are, in this case, both the fracture net KH of the active well and the depletion of the observation well. The different optimized length versus aperture relationships mirror the heterogeneity of the fracture network. That means the variation of the correlation between length and fracture aperture in the different wells and areas of the field, keeping the discrete fracture network realization fixed. We have to remember that the different values of fractures aperture are linked not only to the KH well test, but also to the fracture network characteristics that are intensity, length, and orientation. So for a given fracture net KH, a larger aperture is expected for low fracture intensity and vice versa, small aperture for high fracture intensity. Integrating the alpha values estimated at each well, a possible estimation of the spatial variation in the infra-well space can be inferred. That means that the variation of the length versus aperture relationship is estimated at field scale. Therefore, based on this alpha map, the whole discrete fracture network can be characterized in terms of fractures, effective aperture, and permeability. In fact, a lot of criticalities and uncertainties affect, as usual for fracture study, this workflow. Among the other, we have to highlight that the workflow tries to calibrate the fracture network with the dynamic data, focusing the attention on the fracture characteristics, but keeping the discrete fracture network realization fixed. An alternative approach could be that of considering different discrete fracture network realization and/or different discrete fracture network characteristics. That means different values of fracture length, orientation, and density. This different approach focused on the discrete fracture network characteristics would request several stochastic fracture realization and could be more effective, especially in describing fractured reservoirs affected by a relative low fracture density that are very sensitive to fractures orientation and length. In fact, the combinations of the two approaches iterating between discrete fracture network geometrical characteristics and fractures permeability could be theoretically, although quite time-consuming, the ideal approach, especially for reservoirs affected by a fracture intensity relatively low. Another criticality is that the fracture net KH estimated at the wells represent the target of the workflow, but relies on the estimation of the KH matrix that is uncertain because it has to be referred to the same volume investigated by the well test. However, in a fracture reservoir, the permeability can be very heterogeneous, and this fact is mirrored on the very regular isopotential lines affecting the drained volume by the well test. This fact makes the estimation of the radius of investigation uncertain, impacting on the inferred KH matrix that represent the benchmark for the estimation of the fracture's net KH. To minimize this last issue, several sensitivities about the possible radius of investigation could be considered, ranging from the minimum scenarios made only by the cells crossed by the well path. The total fracture population, characterized in terms of aperture and permeability, is then upscaled into the 3D model grid to get the relevant permeability and porosity values describing the characteristics of each cell. The effective permeability, so upscaled, describes the 3D permeability anisotropy of the fracture system in the three directions affecting each cell. The permeability upscaling process can be performed using different methods, ODA, ODA-corrected, flow-based, etc., that are more or less effective in describing the fracture network connectivity and lead to different results, more or less optimistic. They can represent theoretically high side, most likely, and low side for effective fracture permeability estimation. The flow-based could be assumed as the most likely. The ODA method with infinite fracture length could be seen as the high side estimate, while the ODA-corrected method could be considered as the low side estimate. However, the output represents just the initial input for the flow simulation that has to be calibrated to the dynamic data through two steps, first at well scale and then at field scale. These calibrations are fundamental and in fact minimize the importance of the selected upscaling method because in any case the output has to be reconciliated with the dynamic data.